Yes, talk this evening is about understanding exohexahedra, a very important subject, I think. Next, please. This is a convex tetragon. That's what we call a square. The technical language to define a square is a convex tetragon. And the other figure we would have seen for most of the existence of Homo sapiens on this planet. Would have seen tetragons and triangles and trapezoids, etc., but nothing else. Next. Only in the last several thousand years, and mostly in the last 500 years, have we learned to see these images as three-dimensional objects projected in a two-dimensional space. And what we're really drawing isn't on the paper, it's in the mind. This guy, Louis Neckard, noticed in the 19th century that if we look at this and we see the hexahedron, the front will always become the back, and the back will always become the front. We can never see it in just one way. Next, please. So we've learned to see things, to project these drawings, these images in space. It's from this idea of linear perspective. Next, please. But for most of history, we saw things quite differently. Next. So the whole idea of linear perspective really descends from this guy, Pythagoras. He came from the island of Samos, where he was persecuted by a despot ruler, Polycrates, and then he evacuated with his school to Croton, which is in Magna Graecia, in the boot of Italy. And it was an Apollonian cult. The symbols of the Delphic tripod are always associated with Pythagoras and with the colony at Croton. Next. He gave us what were called incommensurable numbers, numbers without end. This was actually a capital crime to reveal in Pythagoras' day. Numbers such as the square root of 2. Next. He studied nature, and he found this proportion, A over B equals B over C equals 1.6, et cetera, et cetera, et cetera, another endless number, in the natural world. Next. So a sacred symbol to the Pythagoreans was this pentagram, because all of the proportions of the pentagram are reckoned to come out to be this divine proportion. And it was only after the advent of Christianity that we took this sort of mystical, spiritual symbol and turned it into something that's quite the reverse. Nevertheless, these proportions occur in religious architecture worldwide. Whenever she changes, you change. Pythagoras gave us square numbers and cube numbers, which we're all familiar with, but he also gave us triangular numbers and trapezoidal numbers and others which have their uses, but we've just sort of forgotten about them. The Pythagorean emphasis on number came from the idea that the whole world was in fact number, and that all of mathematics, proportions, geometry, all of the laws of ratios and arithmetic were actually the laws of nature. So when you think about it, every character of every text, every crafted image, every symbol that we transcribe are actually their reckonings, their calculations, their estimations. And in this sense, all of art and all of language are in fact mathematic. A few months ago, George Church, the director of my laboratory at Harvard Medical School, tapped me on the shoulder and he said, "Joe, your name came up in faculty meeting. We want to know why we don't have any more well, we don't have enough art around the genetics department at Harvard, and would you come up with some ideas? And so we have this atrium in the new research building at Harvard Medical School with 187,000 rocks in it. I actually didn't count the rocks one by one, but I counted 1 square foot and then how many layers and multiplied. But there are 187,000 rocks. And I decided to number the rocks, but not just with sequential numbers. I wanted to number the rocks with the numeric equivalent of the genome of the apple tree, the tree of knowledge. And look, I knew that Macintosh and Golden Delicious apples had been sequenced. They're among the food crops that have been, their genomes have been fully sequenced. Next. But by looking into it, I found that there was an apple, a wild apple, a species of wild apple that grows on the slopes of a mountain range in Kazakhstan, the Tian Shan Mountains, called Malus cerevisiae. This apple has not been sequenced, and it's endangered, and it's resistant to all of the diseases that domestic apples, that all the cultivars are susceptible to, and it has larger genetic variation than the cultivars because by cultivating the apples, we actually reduced their genetic diversity. So I made a project to put together a project to sequence the genome of the Malus cerevisiae. George Church is using it as a test bed for our new nanopore sequencing, and a company connected with the Personal Genome Project has also volunteered to sequence the whole thing. So I obtained seeds and leaf tissue from expeditions that had gone to Kazakhstan to collect these apples. Next. Now, the whole genome of the apple won't fit on 186,000 rocks. We estimate it's diploid. The cultivars are actually multiploid, but the wild apple is only diploid. And the cultivars have small genomes for vegetables. They're around 750 million bases long, 750 million rungs of the ladder of DNA. We think that the wild apple will have between 500 and 750 million bases, and that's too many to put on the 187,000 rocks in numerical form and still have the numbers legible to the human eye. So I could put some genes, or a gene from this apple tree on the upper layer of rocks, which is 44,000, and so I decided to use this gene from the ancient apple. This is the devil's own apple, the apple of Eden. I decided to use a gene called rubisco. Rubisco is the most abundant protein on Earth. It's, the real name is ribulose 1,5-bisphosphate carboxylase oxygenase. But it's fundamental to all life on Earth. Next. It's involved in the Calvin cycle of photosynthesis. It takes inorganic carbon from atmosphere and turns it into food. It doesn't do it very efficiently, and in billions of years, nature hasn't really been able to improve the efficiency of rubisco, and human scientists have tried to improve the efficiency of rubisco unsuccessfully. But when rubisco appeared on this once barren planet, then all of the verdant gardens of Earth appeared. And so the rocks will hold the record of this story too. Next, please. So geometry really literally means measuring the Earth, geometry. And the more we measure the Earth, actually, the more we find that we're measuring the extent of our own sensorium, of ourselves. Next. The Greeks knew that straight lines could appear to be curved. And so architects even today use a principle called entasis to artificially curve lines to make them appear to be straight. This is happening in the human brain. We've taken this mathematics that we understand, and we altered our planet with this mathematic, but also we alter the way that we see. Next. This was the most important Pythagorean symbol. It's called tetractys. It's a triangular number. It's the number 10. Does anybody see a three-dimensional object in the tetractys? Can you see it? It's there. Do you see it, Carmen?
Yeah, I see it now.
What is it?
It's a square. The two near the top,
Uh-huh.
and leave off the the 3 points,
Uh-huh.
and then it's inside, and it's sort of like a block sitting, kind of pointing towards us.
Exactly.
Its bottom.
It's a cube. Next.
Yeah, cube.
A hexahedron. Next. We'll see when Pythagoras saw this, and he didn't have paper. His numbers were written with pebbles on the earth. When he saw that he could pull a three-dimensional object from a two-dimensional space, project a three-dimensional object in a two-dimensional space, he thought this was incredibly mystical. What do you see in this? Do you see it? Can you see the cube? How many people can see a cube? Good. That's better than most audiences. Next. This is my line drawing of a hexahedron. Same principle. Next. So the Pythagoreans found this mystical action of this like mystical quality of the tetractys, and then they expanded, they asserted all these mystical meanings on the numbers on each of the numbers. This is the Godhead, this is duality, this is unity, and these are the elements. And this tetractys survives. This is on the dollar bill. It's now a Masonic symbol. It is still like preserved through the centuries. They gave mystical meanings not only to numbers but to the geometric solids. And the hexahedron is the Earth, of course, because that's what we thought the Earth was, a hexahedron. Next. Hexahedrons have spiritual meaning all over the world. This is, of course, the Kaaba in Mecca. And before it was the Islamic Kaaba, it was a temple to earlier deities. Next. This is Isaac Newton's drawing of the inside of Solomon's temple, which the holiest of holies was also a hexahedron. And Kabbalistic literature describes the spiritual aspects of hexahedra as well. That's Metatron's cube, which has hexahedra in it, and octahedra and icosahedra. Next. So through the Middle Ages, we preserved this notion of divine mathematics, but with the end of the Roman Empire of the West, we lost the whole idea of linear perspective. Next. In the late Middle Ages, Roger Bacon, a famous philosopher, theologer, he decided that he took it a step further from Pythagoras, that these numbers were not only the laws of nature, but they were the laws of God. And he wrote a letter to the Pope, and he said that the Pope should tell all artists to study mathematics because this is the hand of God. Next. And this guy, Brunelleschi, he rediscovered linear perspective. He received no formal education, and yet he designed and supervised the construction of the largest dome since the classical age on the cathedral in Florence. I'm sorry. Next. And the way he rediscovered linear perspective is linked to the famous baptistry in Florence. He painted a picture of the baptistry and put a hole in the picture that he could look through from the back, and held a mirror in front of it, and then held it in front of the real object in the real world that it was situated in. And from this, it said he rediscovered linear perspective. He didn't write about this. I don't even know if he could write. Next. But this guy, Leon Alberti, he codified linear perspective. He described, and he credited Brunelleschi. Alberti was famous for another famous hexahedron, also in Florence. Next. So, with a few simple rules, you could project three-dimensional objects in space perfectly. You could figure scaling proportion. So if you knew how big an object was, all these square tiles in the front of this picture on the left are the same size, and using these vanishing points, you can determine precisely what the size of something would be at any point in the distance. So if you know how big the building is, you know how big to draw it in the distance using these same rules. You can tilt and turn circular objects like the tufts of dandelion puff using these same rules, and artists did. Next. So Renaissance artists, they rediscovered linear perspective, and you know, after Francis Bacon, they assigned spiritual significance to it, and they used linear perspective to paint spiritual subjects like the lives of the saints and Jesus and such. But inadvertently, they changed technology. Next. The drawing on the left is a pre-perspective drawing from the Arabic literature of a water pump. And the drawings on the right are the same machine, only drawn with linear perspective. And this drawing obviously affected the technological built environment. Next. The first school of arts and sciences was, since classical times, was this school of drawing, school of design in Florence, and art students were taught geometry, anatomy, optics, and philosophy as part of the whole picture. Next. This is a little-known episode in the history of art and science. This guy applied to be the geometer at the Academy in Florence, and there's no record that he was accepted to take that position, but later on he was appointed to the prestigious Academy. Next. His colleagues there in his lifetime published descriptions of the treatment of light on three-dimensional objects and protrusions and indentations on three-dimensional objects. This technique, this craft was called chiaroscuro, and Galileo knew about it. Next. This is from his first publication. He drew with chiaroscuro the objects he saw in his telescope. It's quite obvious that whoever painted these ink washes knew chiaroscuro, and there's no reason to think that Galileo himself didn't paint these things. Next. He called his telescope a perspective tube. He never called it a telescope. Someone else coined the term telescope years later. And remember that while they were making all these important revolutionary discoveries in astronomy, they weren't using telescopes, they were using mathematical tools to measure the sky, protractors and rulers and t-squares, and with these implements, they determined the heliocentricity of our solar system. Next. Got them in trouble, of course. Next. It fundamentally changed the way we look at our own world. Next. Astronomers were still stuck on the idea that mathematics corresponded to the cosmos. Here's Kepler's nested solids, in which he took the Platonic solids and inscribed them with spheres, and just by accident, by the turn of some quantum hexahedra, they actually corresponded pretty accurately with the known planets of the time. So some people say the end of the Renaissance was the trial of Galileo, in which he capitulated. And we tend to forget that the Renaissance was an era of bloody conflict, of horrible strife, of interethnic and interreligious persecution and slavery. Next. All these brilliant thinkers were burned at the stake, sometimes with their books. Next. To date, no truly enlightened society has ever existed, unfortunately. Some people say the end of the Renaissance was really the advent of the knowledge of relativity, because it was the end of Newtonian space. Next. We realized that our planetary models for atoms and such were flawed, that atoms are quantum entities that pop in and out of reality, that the laws of nature were actually counterintuitive, and art responded to this too with hexahedronism, right? Next. Nature loves a hexahedron, and the reason nature loves a hexahedron, next, was another determination by Kepler, is that the best way to stuff objects, spherical objects, the most efficient way to pack them in an enclosed space, next, is to put them into a box. Kepler called it cubic close packing. Next. In biology labs, we put all the secrets of life in boxes. They're like cereal boxes or cake mixes. These days, the stuff I learned to do in the 80s now is like comes in this cake mix. You open up the cake mix and you like open this envelope, you mix it with that, and you put it in this, and then da-da-da, and it comes, you get your result. The problem with this approach, though, is that often mistakes, errors turn out to be artifacts of the kits, and we forget the fundamental knowledge of of what makes the kit work. Next. So this is my friend and collaborator, Liliana Frucht. She's a chemist, a principal investigator. She has her own lab with postdocs and graduate students at Karlsruhe Institute of Technology. And for some reason, she decided she should sit in a box in front of her lab, and she did for a whole day, waiting for her colleagues to come up and ask her why she was sitting in a box. Next. See, to understand exohexahedra, you have to have hexahedral awareness. You have to know about the box that you're sitting in. Next. This is the structural hexahedron that we're all so familiar with. We run up against structural hexahedra physically and metaphorically throughout our lives. When I synthesized DNA to put a map of the Milky Way in the cells of a mouse, we don't have an art department at MIT, so I wrote a grant for a small amount of money, not the maximum amount of money, to help me pay for DNA synthesis to put this map of the Milky Way in the cells of a mouse to our little art lords at MIT. We have a small arts council, and it gives these tiny grants out every semester. And so I applied, and they replied that this was insufficiently artistic, which later they regretted, because parts of their letter were quoted in the journal Nature. But I was really pissed off. I wanted to go yell at them, of course, but I didn't. I kept my temper, and I waited for the next grant writing round, and I wrote a grant to have a series of conversations with a brick wall for the maximum amount of money. And I knew that I would get to go before the entire committee and explain to them why they were a brick wall. Unfortunately, I became a victim of my own irony. They gave me the money, and I had to build a brick wall and organize this lecture series next. But I was talking with my father about it. You know, a brick wall is something that contains the whole history of civilization and technology, the knowledge that we have to build this brick wall. It's these materials that we imprinted our first languages on, our first written words. Next. We know about, we handed down, this is legacy technology, the mixtures of clays and soils that we would, sands that we would fire in kilns, and that technology next, and all of the knowledge about the interparticle bonding, and that the fact that brick walls themselves are vulnerable to moisture and salt next. And all of the atoms that make up brick walls are, come from the hearts of other stars that existed, thousands of miles, thousands of light years away, and eventually they will be scattered into the cosmos into the same kind of distribution. See, when you see a brick wall, you just have to look a little further. That's That's, I think, artistic vision. Next. So, when Da Vinci was born, there was no Renaissance person, no Renaissance figure for him to look up to. He became the Renaissance figure. But there was this guy, Marcus Polo Vitruvius, who'd written this great work in classical times called the 10 Books on Architecture, and that had been lost, and was in Da Vinci's lifetime retranslated back into Latin from the Arabic. And in this, and the frontispiece of the first edition of the book, the first retranslation of the book to Latin, was actually contained these guys measuring hexahedra. Yeah, okay, next. So Vitruvius said, he made a list of things that he thought artists needed to know. He said, an artist has to have talent. You have to be gifted, and you have to have the ability to listen. And if you're gifted and you don't have the ability to listen, or if you have the ability to listen and you're not gifted, well then, according to him, you would never be what he calls a perfect master. Next. He said artists should be good writers. He said they should be skillful draftspersons. Next. He said they should know geometry and optics and be expert at figures. Next. He said that artists should be acquainted with history and familiar with natural and moral philosophy. Next. He said that artists should know music. Next. He said we should know something about the science of law and physics. Next. He said we should understand the motions of the planets and the stellar astronomical objects, and that we should know about the proportions of the human body and know something about the science of medicine. He said that skill, craft, must be accompanied by scholarship. Mens et manus is the motto of MIT. It means hand and mind. He said that knowledge is the child of practice and theory. Is in essence, he was saying that art is also governed by a kind of scientific method. So this is why Da Vinci's image of the range of human motion is called Vitruvian Man. Nowadays, artists aren't encouraged to know any of this stuff, even music and history. Next. You know, we say we're supposed to help our science think out of the box, but what in fact is happening is science is helping us think outside of the box. This is from 1950. It was a neon lamp at Bell Labs. It was put on this fulcrum like a broomstick and swung around, and they had an acoustic lens. And to test their acoustic lens, they made this time-lapse image of the light was on a sonic sensor, an acoustic sensor, so it brightened and dimmed as it got closer and farther from the light, and they were able to make this image of a sound wave. That's cool. You can't tell me it's not art. Next. So when we're kids in school, they teach us about these characters like Brunelleschi and Da Vinci and Vitruvius, and they say, this is the flower of the human intellect. This is what we can become. But see, these ideas are systematically ripped away as we, enter our careers in business or in the business of education. Next. We associate technological advancement with the fragmentation of knowledge. Everything has to be in its precise and concise category. The box is shrinking. Yet artists are still expected to build bridges between things. There's still this we still want to believe in the myth of the universal polymath, and that's associated with art. Next. Artists are still expected to answer all the questions that the oracles of Delphi were asked. We were supposed to reveal the secrets of life. We're supposed to summon the human spirit. Goethe said, artists see spirits first, and after artists see spirits, then everybody else can see them. Next. So it's been more than 2,000 years since the lifetime of Vitruvius, and more than 500 years since the era of Da Vinci and Brunelleschi, and you wonder what Vitruvius would have said now. Art has become kind of debased in my mind. Art is like no longer about it's sort of lost this magical function of, bringing the world into a better place. It's embedded in these systems of wealth and privilege that really have nothing to do with its potential. With rare exception, art is relegated to the fringes of society, and we aren't expected to make contributions across the board. So, no matter how you look at it, artists are supposed to open a window on the world. And you can't open a window on something you don't have a clue about. The fact is, despite all the fragmentation of knowledge and the consolidation of what we consider to be the frontiers of artistic practice, we still have to know everything. We have to have broad knowledge, or we can't be what Vitruvius would call a perfect master. This is the house, and you'd be surprised how few of us know our way around the house. In the 1970s, environmental art gave way to environmental conscience. And environmental consciousness requires study of the earth. We have to know about the earth to have environmental conscience. And this happened. And many artists are involved in environmental practice, and so they must also involve themselves in environmental observation, in environmental research. Sculptors for millennia knew about the geological formations and where to look for them, and what kind of generic examples of stone were available, and what their material properties were with respect to sculpture and architecture. But see, now we know much more about the earth. We know about geological history and plate tectonics. In my lifetime, when I graduated from college, there were graduates in geology who bitterly opposed the notion of plate tectonics. They refused to accept the idea that plate tectonics was a reality. This was like in the 1970s. But now we know it is reality. We know that the orbit of the moon was once different, that the length of the day and the night was once different. We know about our history, the history of the neighborhood. Next. Speaking of the neighborhood, there are 206 nations on Earth. And if I mentioned one of them, like Ghana or New Guinea, you would probably know, many of us would probably know roughly where they were and something else about that. But there are fewer worlds in our solar system, and nobody can mention more than 10 or 15. Next. Did you know there was a world named Ferdinand? There's a world named Margaret. We don't know. We don't know the neighborhood. We don't know our way around the neighborhood. So, my interest in molecular biology 25 years ago brought me to, came from my activities and notions about search for extraterrestrial intelligence, because you have to draw a picture of yourself. You have to have self-knowledge. You have to reveal yourself to yourself before you can reveal yourself to anyone else. Something that we've been trying to do for thousands of years, something we know is impossible. But I found it to be a lush ground for artistic activity. Next. We still have to know about the human body. St. Bartholomew in the Cathedral of Milan is the skinned alive saint. And there's Gunther von Hagen's plasticized Bartholomew. Next. I did an exhibition at the Museum of Natural History in Vienna last year, and they gave me keys to the back room. I was able to go see all these collections of insects and fossils, and that I just blew my mind. I spent much more time wandering around in these back rooms than I did putting up the exhibition. And I found these rows of human skulls and human bones, big rooms full of them, and some of them were painted and actually carved with the names of whoever they were, and it inspired me. It reminded me of Scrimshaw. And so in Australia last year, I used dual X-ray absorptiometry, short DEXA, called DEXA for short, to accumulate three-dimensional data about my own skeleton. I wanted to print out my own skeleton so then I could carve my skeleton like these bones in Vienna, and then save the CNC so that when I died, somebody could throw me up on an anthill, and then there'd be some bones and that they could be carved, and that I could actually become art. But to print out one vertebra took like 90 minutes, and there are 206 bones in the adult human skeleton. Granted, I have fewer, but it was going to be very expensive and very time-consuming to print out my entire skeleton. Plus, the DEXA scans didn't give me really enough three-dimensional data about my skeleton. I'd need a CAT scan, and in the US, you need a medical excuse because it's a large radiation dose, and so I guess I have to go to Brazil. Go ahead, Julia. Yeah. So this fascination with the secrets of life that's defined the history of art has now taken on an undreamed of reality. Next. The body is no longer just the body. The body is an augmented form. It's part natural and part man-made. Artists have to cope with these developments. Next. The whole knowledge of this vast revolution in biology and biotechnology has occurred in our lifetimes, and there's been this new field called BioArt. It was 1958 that Francis Crick described what's called the central dogma of molecular biology, that DNA is translated to RNA, and that RNA is transcribed into RNA, and that RNA is translated into protein. Next. And see, if we're going to keep up with the scientific revolution that's happening around us, with the amazing advances of technology that are going on around us, then we have to know about molecular structure, the molecular structure of DNA. Next. And we have to know what DNA stands for. I know, for instance, that DNA means, in English, deoxyribonucleic acid. I know that in German it's desoxyribonukleinsäure. What is it in Dutch? Huh? Come on. What is it? I assign homework. Everybody has to go home and find out what DNA means in Dutch. It's your language. Okay, next. So BioArt is really amazing. A lot of amazing things have happened. This is Oren Katz and Yonat Zer's worry dolls. They made models, templates from these Guatemalan worry dolls that in Central America, little kids go to bed with these worry dolls and they're supposed to take up all the bad dreams. So Oren and Yonat made it out of nerve tissue. And there's Stellark in his ear. And the mouse from Jay Vicanti's lab at Harvard has become the scary icon of the anti-genetic modification movement, and nobody knows. Like, while they're waving the flag, see how scary this is? It's really scary. I have a friend in Milwaukee who was in this horrible accident with electrical discharge, and he has his face burned off. He has no eyes, he has no nose, he has something like a mouth but no lips. I drink beer with him. Jay Vicanti was growing artificial cartilage and testing it physiologically in the mouse to see if it would work in human beings. And the idea wasn't scary at all. It's to alleviate vast suffering, horrible misery. It's a wonderful and not a horrible thing. And artists, they don't look they don't look deep enough. They don't see through the wall. It's like they're satisfied with scientific data they obtain in the health food store and never crack a scientific journal. It's a sad thing. Vitruvius would be pissed. Next. Now we have these, there are possibilities in the last few years that are just amazing possibilities. We can take stem cells and convert them like it's like a whole menu. You can turn a stem cell into heart tissue, into fat, into muscle tissue, into nerve tissue. You can take a stem cell and convert it into anything. This is way beyond Frankenstein. This is really cool. We have such power over the world around us that we've never had before. Next. You can take the stem cells of, well, maybe I'll get to this later, I'm not sure. But you can take the stem cells of, like, now we've taken stem cells of a rat and decellularized the pancreas of a mouse, stuffed it with the stem cells of a rat, and by some mysterious method, we don't know how it happens, but the rat stem cells receive signals to form a mouse organ made out of rat cells, and then you can transplant that into the mouse and it functions perfectly. This was done, excuse me, in Tsukuba, Japan a few years ago, and then a year later, in California, scientists took human stem cells, decellularized a mouse liver, and grew a mouse liver out of human stem cells, transplanted it into a mouse. Right now at Church Lab, we're trying to turn George Church into a chicken. Okay, so a year after Francis Crick announced his central dogma, this guy C.P. Snow, who was a physicist, he wrote his famous book on the two cultures. He was a physicist, but he liked to hang around with his friends in the humanities. And at one of their parties, he posed the question, what is the second law of thermodynamics? And not only did they not know, they got angry with poor C.P. Snow. And C.P. Snow was like asking them if they knew how to read. Does anybody here know the second law of thermodynamics? This is 19th century physics, ladies and gentlemen. The second law of thermodynamics. Next slide, please. There will be no excuse for us not to know these fundamental things. This is our world. We live in this world, and we have a responsibility to make art with immediacy that's relevant to the lives and the functions of the world that we live in. So the first law of thermodynamics is called the zeroth law. It's when there are two bodies in thermal equilibrium with the third body, that they are also in thermal equilibrium with each other. The first law is you can't win, the second law is you can't break even, and the third law is you can't get out of the game. These are fundamental, means there's no perpetual motion. Work and heat can't be separately conserved, that entropy cannot be decreased. These are fundamental, this is fundamental knowledge. And this should be fundamental knowledge for art and science. Da Vinci and Vitruvius, they didn't know anything about electromagnetism. Next. This guy had a passion for drawing, wrote poetry, and spent years trying to figure out color theory. He also gave us these four famous equations. Next. These equations, Maxwell's equations, describe the relation between magnetism and electricity, and most importantly, it also explains the propagation of light. And light is not only visible light, light is radio, because radio waves are photons. Did you know that you could if it wasn't for this guy, Maxwell, we wouldn't know that you could make a photocell with a sugar donut. You can take the sugar off the donut and put it in a coffee filter and pour water through it and then clean it with alcohol, and then you have titanium dioxide. And titanium dioxide is a good diode for a crystal radio. It's also photoelectric. You can make solar cells out of sugar donuts. I make radio crystals out of heat-treated steel wool. I've never seen this described in the literature, but it works really well. It's a very sensitive detector with heat-treated steel wool and pencil points. Next. You can mine radio crystals from beach sand with a magnet. You can make diodes and variable capacitors with solutions of baking soda and cream of tartar, which is a byproduct from winemaking. Next. So, next. So these are some of my crystal radios. This is you know those toys that you put your hand in or you put your face in. There's these pins, and then you take your hand out, and there's an impression of your face inside it. I added an electrical conductor and an insulator, a dielectric, and to use as a capacitor. And it was a very, very sensitive variable capacitor, more sensitive than the kind of capacitors that move plates in and out of each other. And I've never seen this described either, but I used the same principle to make voodoo capacitors for my voodoo radios, which you tune by pushing and pulling pins in the voodoo dolls. Next, please. I used genes from a marine sponge with my colleagues, the late Tara Gianolis and Ido Bachelet, who's now at Bar-Ilan University in Israel. And we created the first bacterial circuits made entirely out of bacteria. Some of the genes were optimized to chelate, that is to plate conductors, and some were optimized to plate semiconductors, and we applied them in the appropriate places in the circuit and had varying success. Next. They were written up in the journal Science. Next. Incidentally, microvenus, my first project in molecular biology, was cited in Science in September 29th. It was the print version of Science that was published September 29th. Contains an article by the scientists who made the first full book in DNA, text and pictures, and microvenus was credited in this article as being the first successful human intellectual information committed to the biological medium. And I'd written that article that was cited in Art Journal, you would call a scholarly publication of the College Art Association. It's an association of U.S. college faculty. And it was the first time that Art Journal was ever cited in Science as well. I'm particularly proud of that. So it's not just about radio. This is a crawler that crawled around the Mojave Desert in Owens Valley, California, made out of a cash register and conveyor belts. And this is my sand counting machine from an exhibition in Athens. Next. Alexander Graham Bell discovered optical communications. He was the first guy to transmit human voice on beams of light. He didn't have the detectors that we have now. He didn't have semicrystalline silicon solar cells or LEDs. He had selenium cells, and he writes about how he made an excellent photodetector out of cigar ashes. Now, I don't like cigars, but I have smoked a lot of cigars trying to reproduce Alexander Graham Bell's, and I have never figured it out. Somehow, there must be, it's a mystery. I leave it with you. Next. But I was interested in these principles. I made a car guitar, which wasn't supposed to work. Because of the successful car guitar, I modulated a heavy filament car headlight with a high fidelity musical instrument, human voice and such. And because of that, a professor of physics from Harvard came to visit my studio, and he went, "That's not supposed to work, you're tricking me." "No, it does work, look." And he went, "Oh my God, you're delivering the physics colloquium next week." And I did. And I did the sort of cardinal sin where you're not supposed to bring an experiment into your talk and make it work, but I brought it in and I made it work, and it worked. I made all these light casting devices out of old tape recorders and flashlights. Next. In Stockholm, I covered a young woman with honey to protect her skin, and then gold leaf, and used direct current light to bounce light off of her. If you use AC lights like this, you'll hear, in this case, you'd hear 50 hertz. Hurry, this is 50 hertz. And, but direct current light is pure. So with this device, we were able to detect, by just the light that bounced off of her, we'd be able to detect heartbeat, voice, respiration. The point is that we imprint ourselves on everything that we encounter. It's like a thermodynamic soul. We imprint ourselves even on the light that bounces off of us. Next. So this is a crystal radio. It is the most fundamental electrical circuit. This is the coil, this is the capacitor, this is the crystal, and these are the earphones. These symbols are universal. If I show this diagram to somebody who speaks Chinese and no English, or French and no English, or French and no Chinese, they see these are universal symbols that are known all around the world. They're fundamental to all electrical circuits. Next. And art can have, as I said, no immediacy or no relevance unless it's constantly refreshed, invested with new symbols and new systems for understanding the world, or we risk becoming obsolete. Art is not just a visual language. Next. It's a language of ideas. And ideas means you have to think. It's not automatic. It's not all automatic. It's not all gesture. It's about how we accumulate and how we process knowledge. Next. These are Da Vinci's methods for drawing, inscribing parabolic curves. There is absolutely no reason why artists shouldn't be as rigorous about what they do as anybody else is about what they do. Next. Can you see the cube? Can you see the cube? How many people can see the cube? Okay, next. If you use that same faculty that you used to see the cube in the last figure to see a three-dimensional object in this figure, you see an object that cannot exist. You see an object that exists in more than 3 dimensions. This is a heptagon. Heptagon is very mysterious. Next. Odd-shaped polygons in general are very mysterious. This is a spider coil that crystal radio hackers love because it's a flat coil. Next. It has the same function as the cylindrical coil, but it has to have an odd number of sides. It can't be made with an even number of sides. But if you want to make one, let's say a 7-sided spider coil, you have to go online and find somebody who has a template because you can't construct one with a ruler and a compass. These are the perfect polygons. These can be constructed with protractors and rulers and the mathematical tools that are familiar to us. Next. 360 is a nice number. It has 24 factors. That means we can make, something teen polygons perfectly because they come to exact points on the 360-degree protractor. Next. Does anybody know why there were 360 degrees in a circle? It's because Gilgamesh and all these guys believed that the sun revolved around the earth in 360 days, in 12 30-day months. And we know that's wrong now, but the Greeks adopted it. Next. And that's why we use 360 degrees to measure direction, time, location, not only location on the earth in terms of latitude and longitude, but the celestial sphere as well. Next. So these are the easy to make polygons with our 360-degree protractor, but all of these have these fractions that keep on going and just go. They don't. Many of them don't end. You have to only estimate where this point is, and it's like shooting pool. So when you're shooting pool, and whoever you're playing with is goes over and aims at the cue ball, they make an estimation. Then they go over here and then they aim at the target ball in the pocket that they're shooting for, and they make an estimation. And that person will always under or overestimate the shot because they'll always under or overestimate. You worry about who shoots from the hip. Next. So if you're trying to make a heptagon, a 7-sided figure, and you estimate where the points are in the heptagon, and you blow it up to architectural scale, where you're always going to have a gap or an overlap because the estimation will always include an error. Next. This guy, the great German mathematician and philosopher Albert Dürer, tried to figure out a way to, actually published his way to make a polygon, a 7-sided polygon with a compass and a ruler, but it was flawed. It's an irregular polygon. It doesn't have equilateral sides. See, we're stuck. We're stuck with the tools we have. Next. And the tools we have determine the built environment around us. Nature makes heptagons. This is a heptagonal fullerene, carbon molecule. There are many heptamers, perfectly 7-fold symmetry molecules in biology. Next. There are 7-fold cacti. Next. There are 7-fold sea stars and 7-fold fungi. Next. But human beings are out of luck. Now, I'm going to give you some secret information that may be useful in the future. For some reason, all beer caps on the planet have 21 divots, 21 little points and 21 little divots in them. All beer caps. With beer caps, you can make a perfect heptagon because you make sure that you have the same number of divots in each one, and then you have a perfect heptagon because it's 21. But 21 is one of those enormous fractions. So whoever figured this out, it was like tough job. But it inspired me, so I made these magic rings that you could like put together. Next, it's like they're jewelry for nerd girls. I thought, because we have a lot of nerd girls at Harvard and MIT, I thought I could, augment my artistic income. Next, but you like assemble them, and you can make, if you count all of the integers like the beer caps, you can make all these figures. The problem is it's tedious, and so I wasn't satisfied. Next. I made protractors not with 360 degrees, but with thousands of degrees. Like for multiples of 7, you need a protractor with 2,520 degrees. The problem is, next, even the most advanced computer software, you have to round off to hundredths of a degree 360, and then you end up with an error that accumulates. So I error corrected to 10,000ths of a degree so that none of my integers, none of these increments are more than 5,000th of a degree off, and that's a minuscule variation, thinner than the thinnest pencil point. It's pretty good. So then I made these sort of extra 360, beyond 360 polytractors for multiples of 11 and 13 and others, and then I reduced them all to these new tools. Next, these are my polytractors. They have increments on them with 5,000th of a degree accuracy for all polygons, in this case for 3 to 28. Next. There's a 0 line and numbers corresponding to the sides of the desirable polygon. To work them, you just line up 0 with the side of the number that's the side of the polygon that you want. So 0 to 7, then 0 to 7, then 0 to 7, and you get these intuitively and perfectly. These are really cool, fun. And you can like automatically create things that you would have to like do a lot of arithmetic for. You could do really easy. I laser cut these. I laser cut them in lab, and I was trying to figure out to explore how I could, because I want to give them to the world. You think every fabricator needs them in their toolbox. Every carpenter with their speed square, they need to be in, every graphic designer needs these. Everybody who makes tiles and mosaics and stained glass need these. They need to be in every children's museum, and every science museum, and every hardware store, and every graphic arts store. But they cost me too much to make. They cost like $8 a piece with materials, and I need to make them for 50 cents each. I need to make them for the whole world. I mean, ultimately, if nothing else, I'll turn them into beer coasters. You're welcome to come up and try these after the talk. Next, please. Yeah, they work really well. So you line up, here's the heptagon, you line up 7 with 7 and 0, 7 and 0, and if you use a straight edge, it's perfect every time. Next. So, tired of the same old built environment? Next. I learned a long time ago that if you build a bridge, it may be 20 years, but if you build a bridge, sooner or later, somebody's going to walk across that bridge. How do we build the city of the future? We give them the tools. Next. So, one of the things that came about after Vitruvius and Da Vinci and Michelangelo was photography. Although camera obscuras were known well before the era of the Italian Renaissance, it took 500 years for somebody to put a lens on the camera obscura. This is a camera obscura view of the baptistry, the famous Brunelleschian baptistry in Florence. Next. And cameras way preceded photography. They were developed by artists as drawing tools. And so, next, when these guys came around with their bitumen and lavender oil, like dig it, bitumen and lavender oil, this you can find in the classical makeup box, bitumen for doing your eyes, and lavender oil because it's so fragrant. That's the first photographic emulsion. It was in every lady's makeup box from the time of ancient Egypt. It's amazing. We forget. So when they came around with their photographic emulsions, the cameras, we already had the cameras for them. The classic Kodak hexahedron, the lunar hexahedron. Next. In lab, we use, there are many light-activated reagents. This is green fluorescent protein, which has become a fundamental tool in the time that I've been in molecular biology. It's an 11-sided, it's one of those, doesn't conform with 360, it's 11-sided, it would be hard to draw. Next, an 11-sided protein. And it's become a real fundamental tool in many aspects of molecular biology. And at some point, 10 years ago or so, I thought I should try to use these reagents to increase the resolution of conventional photography. And so I used a vitamin precursor from breakfast cereal called biotin that always sticks to DNA with an azide group, and that allows it to stick to DNA only in the presence of visible light, and it's really fast. So, and the cheapest commercial source of DNA is actually sperm, fish sperm. If you want just generic DNA, you go to the fish market and you get fish testes, and then, which are mostly consisting of sperm, and then you lyse the sperm and you swing out the cell trash, and what you have left is DNA. And then we sonicated it to make it into short pieces and laid it on substrates, glass and nitrocellulose. Next. And then exposed it to light with photobiotin to get the biotin to grab onto the DNA. And then this protein, streptavidin, which is a protein from Streptococcus, grabs onto the biotin, and then alkaline phosphatase, or horseradish peroxidase, next slide, grabs onto the streptavidin. And then on these substrates, you add some colorimetric agent. Most of them are completely unpronounceable, even by me, or you can use nanogold particles next, and that you end up with this stack of materials, DNA, photobiotin, alkaline phosphatase, horseradish peroxidase, da-da-da-da-da-da, and the whole stack is orders of magnitude smaller than the smallest silver halide grain used in conventional photography. And so the images were of microscopic resolution. Next. These are some of the images photographed from microscope slides. Naked girls, DNA waiting all this time to be revealed. She is Eve. Next, please. Renaissance, it took the advent of photography for us to realize three-dimensional photography was possible, that we could make stereo images. Next. And using if you cross your eyes, most biologists know how to view stereo images without the machine. If you cross your eyes until you see two fingers, or if you hold two fingers together and you cross your eyes and see the little hot dog between the two fingers, if you cross your eyes until you see three of these boxes instead of two, the center one in this case will have a square underneath the surface, and this one will have an image on top of the surface. It's skill. It's teaching. It's learning how to see. It's sort of where it's a remake of linear perspective. We have to teach each other how to see. Next, these same tools. These are applied to digital technology too, to create stereo images, and this is anaglyphics, how we watch the movies, the 3D Godzilla movies and such. But these same tools are the tools we use to visualize the subvisible molecular world. Next. These are the kind of illustrations you find in Science or Nature every time you open up the book, open up the issue. Next. Liliana Frooke again, this is the chemist in the box. She and I have a project this is the largest protein structure that has been resolved to date. It's a yeast ribosome. And if I had a chalkboard here, or if they let me draw on the walls, I'd explain what a ribosome is, but it's important in the central dogma about the translation of RNA into protein. And we use all these, because remember, they're not planetary, atoms aren't planetary objects, they're quantum entities, and we use these formalisms to describe what they are. We use ribbons and coils, and we use van der Waal radii, and we might try to look at them as geodesic points, but or fractals, whatever mathematic we use to describe them, it's a grid that we put in front of what is reality. And so we decided to use atomic force microscopy. Atomic force microscopy, these are very tiny little needles in the stylus of an atomic force microscope to carve the structure, the negative structure of proteins. So ribosomes have two major subunits, and generally all proteins interact with each other not because of charge or because they're hydrophobic or hydrophilic, but because of the shape, because they fit perfectly. It's like sculpture. And so we wanted to use, van der Waal radii, geodesic, different methods of looking at our different formalisms, and make like an ice cube tray next, and then next, please, and then label the proteins with markers, so we'll see which one fits best, which one has the most protein in it. Then we could have a window on the way we draw proteins, which is a better way to draw them. But also the implication is synthetic protein, and that's exciting. Next. So now we know that we don't have to depend on linear perspective to project three-dimensional objects in space. Holographic hexahedra. Lasers next. Lasers are fundamental. They're ubiquitous around us these days. We run into them all the time. They're in the grocery store. They're in your CD player. They're everywhere. Lasers. They're the carpenter's level. They're the carrier in optical fibers. They're everywhere. And if we want to understand the world around us, we need to know something about stimulated emission of radiation. This is my holographic paintbrush, where I imprinted different kinds of different sides of thermally manipulable substrates with holograms that worked at different angles. Next. In the 70s, we artists were big on laser art, and because we were very unconscientious about the use of lasers in the United States, the strictest regulations for the use of lasers are for art and light shows, and not for science. Next. But it's not just about light shows. These are internally carved acrylics. I carved at Bell Telephone Laboratories in the University of Cincinnati Medical Center in the 1970s. And this one went as a unit opener in high school science textbooks all over North America in 1974. And that was cool because I was expelled from 3 high schools and they were using my book. Next. I explored the use of lasers for carving stone. I mean, both of these things are done now. In general terms, you can buy a block of acrylic with a laser-carved Eiffel Tower in it. In Paris, you can go to the souvenir shop and get a stone that has hope engraved in it. But when I did these things, no one had ever done such a thing before. I remotely controlled lasers from over 1,000 miles away and let little kids draw on stones. But this, again, is another story. Next. I'm currently fascinated with the simplest laser, really. It's called a T laser, transversely electrified atmosphere. You need the same elements you need to create a crystal radio. You have to have capacitance, you have to have inductance, and you have to have a semiconductor, a high voltage diode. And if you just rearrange it, if you arrange all that in one way, you get a crystal radio. And if you just take it apart and make it into a different configuration, you get a laser. Instead of the tank, instead of the standing wave that amplifies the part of the radio spectrum you're listening to, it electrically activates nitrogen in air and causes these electron transitions and emits photons all of the same wavelength, and you get laser light. So my father died in a hurricane. My brother died in a hurricane. Katrina wiped away off the face of the earth the houses of my relatives, the relics of grandma, and all the pictures and books and a lot of my art. And the girl I took to senior prom died in a hurricane, and that same year, in fact. Next. And so I've designed this 106-foot tower. This is our engineering model that's designed to be struck by lightning, and that then it causes and the spark gap controls the speed of the circuit, and these are inductors that couple the masts, and in between the masts is the discharge cavity, and so what happens is this invisible, it's ultraviolet, 337 nanometers. You get a laser discharge through the natural storm in a straight line, and that's like Benjamin Franklin flying his kite. You have briefly, you have an electrical conductor to ground, and so that precipitates a huge discharge from the cloud that in turn propagates this vastly powerful, profoundly powerful laser discharge of the kind that we would need to propel solar sails to other planets. The sun isn't bright enough by itself to propel a solar sail even to the outer part of our own solar system, a light sail. We need lasers like this for that. We need lasers like this to deflect incoming asteroids that could cause the end of life as we know it. And there are no moving parts. They can be rapidly produced. Next. I have this idea that I want to build it as a hurricane memorial. I mean, it's not just the hurricanes that hit where I come from in Mississippi, but hundreds of people die every year in the region from hurricanes, and I want it to be like Ahab grabbing onto the jaws of the whale, raging against God and nature and hurling energy back in the sky, take that, that's what I want. And you would see it for miles around because the secondary lightning discharges wouldn't be stepwise lightning discharges, but rather the straight line discharge back to the laser. So I tested it 150 miles. I did all the engineering for this, by the way, at Hochschule in Bremen, and there, at least for its precursor project. And we tested wind loading at 150 miles an hour at the Wright Brothers wind tunnel at MIT next, and at the million-volt Van de Graaff discharges at the Museum of Science in Boston. I had to modify because even 1 million volts is orders of magnitude. Like the weakest lightning ever measured was 70 million volts, 100 million amperes, or 100 million volts, 70 million amperes, something like that. But this orders of million volts is orders of magnitude less. So I had to modify the electrodes to account for that geometry, and I put UV emitting phosphors along the discharge path. And so I don't think there's unambiguous evidence of emission, but some evidence of emission. Next, please. Right now I'm working on a 32-foot model that will be the first actual lightning pumped model that will be installed on Otto Pina's farm in Groton, Massachusetts, hopefully sometime early spring. Next, please. I use lasers to create audio microscopes, which some of you may have read about. I have a few movies. If you have time, I'd like to play some. Can you trade places with me? Thanks. This is a Abbemuseum. Come on. This is a stentor. This is a pile of rotifers. They're noisy. I just put away the nematode. Oh no. This is a slightly larger creature. It's usually around 930 cells. It's a worm. Having lunch. Should come out in a minute. Yep. Anyway, these are bacteria and protists. They sound like a herd of buffalo because there are millions of them, like herds of buffalo. And of course, I have many more. Next, please. Some still frames. We needed to turn the lights off. I noticed that you couldn't really see what I was projecting, but so I used spectrum analyzers to analyze the audio signatures of different microorganisms. These are generally, this is the transit of the organism across the field of view, and this is Paramecia. This is the signature of the cilia, the millions of cilia. And it's interesting too. I found that I got a similar signature from Paramecia of different species, like Paramecia micronucleate. Paramecium caudatum, Paramecium macro. Anyway, different species that have different, slightly lengths of different cilia, and they leave a slightly different signature, and I could actually tell them apart. Brine shrimp have these wing-like structures that they flap around. They sound like birds, and they leave this double signature. Next. Rotifers are really noisy. They overload the system, and so I could mix them all together and then tell you what was it by looking at the spectrum analysis. I could tell you what was swimming around. Next. I learned to grow all these pond organisms. I was needed to become a farmer to grow, and I've also measured bacteria and tissue and have signatures for all of it. And several of these instruments have been built now for strictly scientific purposes. Next. But there is an opera under the world. Of course, Da Vinci and Michelangelo didn't have computers. I was, graduating from college when the first personal computers hit the streets, and I remember how much artists hated computers. My friend's faculty at the Rhode Island School of Design said, "We will never have computers at the Rhode Island School of Design. It's inhuman." Da, 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 da. They hated, artists hated computers, just like many artists hate genetic modification these days. Eventually, they'll come around. Next. With the advent of computers, video art evolved. We got media art. What's interesting to me is that media art too will become, if not already obsolete, will shortly become obsolete. What's going to happen in your lifetimes when whatever replaces the internet comes around? Next, please. We had to revisit what virtual reality, we had to revisit questions about what reality was in the first place, which problems which we've never been able to solve. We have to consider these problems. We had to consider fundamental philosophical problems. Next. We have, in the lifetime of Vitruvius and Da Vinci, in the lifetimes of Da Vinci and Michelangelo, all of this great font of information was being retranslated back into Latin from the Arabic literature, from Byzantium, flowing back into Western Europe. And now we have this incredible source of information all the time, 24 hours a day. Who uses a dictionary?
Just like
Well, you don't have a spell checker?
yeah.
Okay.
Telephone book.
Examples. Next. We now have these powerful personal computers and smartphones, and these things have fundamentally changed our lives. Next. I divided this talk into two parts because I didn't want to really kill you. So I'm going to give you a break to go get coffee or a cigarette for 5 minutes, and then I'm going to finish the talk. It's a shorter, the ending is much shorter than the beginning.